So before the break, we said that each unit will have an activation function, and that activation function is nonlinear. Now, why does the activation function has to be nonlinear? Actually, this is a very important point, because if the activation function was just a linear function, then any combination, no matter how deep the network is or how complex the structure is just going to only be able to represent a linear function. Okay, and that's where the key to the power of deep neural network comes from, is from the nonlinearity in the activation function. So this nonlinearity then is what allows very large networks of units to represent essentially any function. So the universal approximation theorem says that a network with just two layers of computational units, the first nonlinear and the second linear, can approximate any continuous function to any degree of accuracy we desire. Okay, but remember that's overfitting, right? That's the past. The bottom line is how well it's going to do in predicting new data points. So because activation functions are so important, then a variety of different activation functions are used. The most common are the logistic or sigmoid function, which is represented with sigma of x. So for any input x, we do 1 over 1 plus e to the negative x. The rectified linear unit, or ReLU for short, essentially it's a max between 0 and x. So as you can see, it doesn't take any negative value. It's just max of 0 and x, meaning for any input that's negative, we'll use a 0. And for any positive x, we'll use the actual x. There's also the soft plus function, which is a smoothed version of the ReLU function. So soft plus of x is log 1 plus e to the x. And then, as you can see, the derivative of the soft plus function gives you the sigmoid function. Now, the derivative is important because we're going to apply, of course, gradient descent to minimize the loss. So that's where the gradient comes in. And then you have the hyperbolic tan function, which is tan h of x e to the 2x minus 1 over e to the 2x plus 1. And the range for this function is negative 1 to 1. So you can look at the shapes of these functions in your textbook. They will have a graph of each one of these functions just to understand what's the difference between them. But the idea is they're all nonlinear and they all work. And of course, there are a lot more functions. You know, people publish papers with new functions and, for, better properties, better gradient, faster conversions of the neural network and so on. So there are always new activation functions that come in. Now you can couple multiple units together in a network, which creates a complex function that's a composition of these units. So if I have two units, one after each other, and each of them has a sigmoid activation, then you can see how complex the final output will be. So the first unit will apply sigmoid to its input, and then the second unit will apply sigmoid to the output of the first unit, which was itself a sigmoid of the input. So you can see that it's going to be very complex. So if we look, for example, at this network, so this is a function, we'll give it the name h sub w of input vector x. So it's parameterized by the weights for each one of these units and maps we have the input vector here that has two components, x1 and x2. And we have one output, which is y hat, which is a scalar. Now, the internal structure of the function mirror the structure of the network. Okay, so you can see here, for example, for the first unit, it will have a bias term, which has a weight of W0, 3, and it will have a weight W1, 3, which is the multiplier. We're going to multiply input x1 in this unit number 3 here. And then it has also an input, which is x2, which will have a weight W2, 3. All of these combined with their weights, I add them and then apply the activation function G3 of that specific unit, which could be anything. So we say that this network has one input layer, which has x1, x2 as input, one hidden layer, which has two units in it, 3 and 4, and then one output layer, which combines the output from unit 3 and unit 4. You can see that output is just combined linearly. Actually, no, there's an activation function G5 here applied as well. So that helps you determine if you want the output to be probability, you want the output to be continuous value, what do you want the output to be, and then that generates the output. So this is the unpacking of this network right here with all the operations that take place inside this simple network right here. So the summation and then the activation. Same here, summation with weights and activation. Now, all these weights are learned parameters. So we're going to compare that output to the true output and get the loss for a given input, and repeat that for all the inputs and try to find the weight, all these weights that minimize the loss function. And we would have trained the network then. Okay, so a more general way to think about the network is computational graph or a data flow path, okay, which is what's on the right here. So this is the typical book representation of a neural network, but this is the computational graph or data flow representation of the neural network, okay, which makes clear what computation take place and what's the input and what's the output for each step in the computation. So the weights can be adjusted then to make the output y hat get closer and closer to the true value y for a given input. And then we apply the same training process using gradient descent as we did with logistic regression and minimize our loss function. So each weight is like a volume control knob that determines how much the next node in the graph hears from the particular predecessor in the graph. So you can see that if say I apply a regulation to minimize overfitting, and then a specific weight goes to 0, for example, weight 1, 3, for example, this tells the network that, okay, you don't need to worry about the input x1 when applying the function g3 here, okay, because it's not really important. So the weights here essentially tells the network at each node how much the input from coming to it is important in predicting the next node. So gradients and learning, so we've seen that before, of course. Okay. So we will generally use big matrix W to represent the weight matrix for this network. And we'll use a subscript 1 to say that these are the weights of the first layer, which in that case W13, W14, and so on. And we'll use subscript 2, superscript 2, for example, W2, to denote the weights of the second layer. And then, as you can see, G, we'll have a vector G of 1, which is the activations of the first layer, and then G of 2, which here has only one component, which is the activation of the second layer, and so on. So our loss function will be, in this case, we use L2 loss function. Essentially, we take the summation of the square difference between the target value y minus y hat. So in this case, essentially, we're trying to predict a continuous variable. This is not a logistic loss function that could be used in classification. This is for predicting a specific variable. Now, backpropagation, you will hear that term again soon, essentially is the way that the error at the output is passed back through the network. So if you remember, to apply gradient descent, we're going to have to take the derivative of this loss function with respect to every parameter in the network. And this network right here has all these w's. So 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 parameters. So we're going to have to take the derivative of the loss function with respect to each one of these w's. And to do that, we're going to use what's called backpropagation. So that's essentially was the missing piece here to be able to allow us to minimize the loss function. One more thing, just before we move on to encoding and so on, is that this network you saw right here, of course, is very small and shallow, right? It's just one hidden layer. But essentially, the same idea will apply to networks that are much deeper than that. Okay, so we will just construct computation graph and adjust their weights to fit the data. We also call this function right here, this network fully connected, meaning that every node in each layer is connected to every node in the next layer. So this is the input layer. It has 2 nodes. Every node is connected to every node in the next layer. And this is the output layer. Every node in the input layer is connected to the output layer as well, to its activation. So this is the default design for a neural network, but it's not required. You don't have to have a fully connected network for every problem. Okay, I'll see you in the next part.